So next talk is given by Shu Lin, telling us about the polarization rotation. So please start.
Okay, thank you. So first, I'd like to thank the organizer for bringing us such a great workshop. And it's really nice to know so many new developments in the field, and I've been benefit a lot from it. Today, I'm going to report recent work done with Defu. It's on the polarization rotation of chiral fermions in a vortical fluid. Let me begin with these two figures. And on the left, this figure has been shown many times in this workshop. And it's a measurement of lambda polarization as a function of activation energies. And net polarization has been detected experimentally. We have seen in this workshop already, we have achieved very good agreement between theory and experiment, except there are still some standing puzzles in the comparison. So one thing that might play an important role in converting the orbital angular momentum of the fluid into the spin of particles. And we have also heard a very comprehensive talk by Mamoru that this is a spin Hall effect by having an electric current along one way, and the spin current can be generated for certain materials. And we have seen that the spin orbit coupling also plays spin Hall effect. So these gives the basic motivation that we need to understand the interaction better. So I will discuss today one particular effect of interactions, which is the polarization rotations. Here's an analogy with polarization, optical rotation in optics. So this is a picture of generation of unpolarized light. After it passes through a filter, it becomes polarized. Pass through a medium. So this medium has to be chiral. And due to the asymmetric interaction between this polarized light can be decomposed into right-handed and left-handed component. And these two components interact differently with the chiral medium. So as a result, the polarization axis gets rotated. And this is a polarization rotation in optics. And actually, this technique has been widely used in sugar industry.
Sure. I'm sorry to interrupt you, but sometimes your voice is stable, and so it's better to turn off your video.
Yes. I will do that. I hope it's better now.
Okay.
This is polarization rotation in optics. Actually, it has been widely used in sugar industry because sugar is the sugar molecule is chiral, so it interacts differently with different polarization of light. Consequently, people use this technique to measure the concentration of sugar in certain materials. We actually have a good analogy in quark-gluon plasma. So we know that strong vorticity has been produced in central collision of fermions. And we also have where the chiral fermion interact with polarized medium, the medium polarized by vorticity. So the interplay of here, the polarization of chiral fermion will get rotated, as I will explain. So here's the outline of my talk. So first, I will discuss kinetic theory in spinor form. this is closely related to many talks in this workshop. Then I will give kinetic description of vortical plasma. So then I will move on to talk about one particular infrared divergence from Coulomb's. This actually allows us to decouple the kinetic theory for hard photons. So then after doing that, we are left with kinetic theories for for fermion only. By using that kinetic theory, we calculate vortical corrections to the collision term, and then it leads to the polarization rotation effect. So finally, I will conclude and give outlook. So this is, let me begin with kinetic theory with spinors. So this is a Kadanoff-Baim equations I will mainly talk about the kinetic theory for QED, and I will also generalize it to QCD. So this equation is written in spinor form. Here, all the spin information is encoded in the matrix form. So this Wigner function is the same as what people used in kinetic theories. And in fact, this kinetic series has been used around 2000, but for spin average versions. So what people at that time do is they average over the spin on the left-hand side and right-hand side. So the left-hand side, so the Wigner function becomes simply represented by a scalar-like distribution functions. And the right-hand side, after the spin average, the collisional kernel becomes spin independent. So this is a quite successful spin average kinetic theory, which has been applied to describe shear viscosity and conductivities, etc. So now we are, now we have different motivations. Since we can, today we can measure spin polarization in different contexts. So we need to know spin-dependent transport. So this requires the use of spin-dependent kinetic theories. So the kinetic theories actually has many different forms. We have heard many great talks in this workshop. So I will mention the relation of the kinetic theory we use and to the others. So one main class is the kinetic theory using free particle basis. It dates back to 2000, I think it's 2012. This is a typo. So people decompose the Wigner function into the Clifford algebra basis. And recently it has been generalized to include interactions. And for that, you need to decompose the self-energy into the Clifford algebra basis as well. So we have heard many nice talks yesterday on this subject. And of course, you can also use other bases. For example, if you have a strong magnetic field as a background, so we can have a different power countings. We can use the lambda level as our basis, as our quasi-particle. So for this approach, actually the power counting is slightly different. So here the magnetic field is counted as a gradient zero quantity or h bar zero quantities, and electric field and the vorticity is counted as gradient one quantities or h bar quantities. So this is another possibilities. Also, there are kinetic theories derived using effective field theories, like high density effective theory and the on-shell effective field theories. There, people use a different degree of freedom. Like for high density effect theories, it's fermion plus and a small component of anti-fermions. For on-shell effective theories, these authors use the rotated fermions as degree of freedom. So what our approach is closest to the first kind, except that we don't decompose. So in certain cases, it might simplify the calculation because for a given setup, not all the components are excited. So since I'm going to focus on QED or QCD, I will just give a brief review of the known stuffs in kinetic series in QCD. There are several scales in QED. So first of all, when the particle energy is on the same order as temperature, so this the quasi-particle is not affected by self-energy. At this order, the self-energy can be ignored. So we will refer to this kind of quasi-particle as hard one. At lower scale, when the energy is of order ET or GT for QCD, and then at this scale, the self-energy becomes comparable to the bare energies. So in this case, the quasi-particles needs to be modified. The energy shell needs to be modified by self-energy. So at this scale, the quasi-particle becomes we will call this particle as soft particles. And also at the same scale, electric field gets screened. Beyond this scale, electric field is screened. At an even lower scale, when the energy of a particle is of this order, e to the fourth t log E inverse, or replacing E by G for the QCD case. In this case, it's actually set by is a scale of the inverse mean free path. So in fact, at this scale, we can no longer talk about quasi-particles. And this actually also sets the scale of the gradient in our following discussions. In fact, scale due to non-perturbative dynamics, and at scale of energy, scale of G squared T, the chromomagnetic field also gets screened. And there's also one more important fact that will be relevant. So this is it is the following. So the self-energy for soft particles, meaning this kind, the soft particles, is actually dominated by its interaction with hard particles in the medium. The reason is the hard particle has larger phase space. So for this reason, since the soft particles is entirely determined by hard particles, it's sufficient to keep kinetic theory for hard particles only. So these are well known in QED and QCD, the spin average version of kinetic series. So what we will do is we will keep the spin structure in both Wegener function and self energies for spin dependent transport. So now let me give a kinetic description of vortical plasma. So to simplify the setting, I will turn off the electromagnetic field and also choose to work with neutral plasmas. The reason is if we have, we of course have vorticity in the mediums. So if the plasma is charged, it will generate a magnetic field. So we want to avoid this induction for simplicity. So this is the left-hand side of the kinetic series, and I set the right-hand side to 0 for now. So this equation can be solved perturbatively in gradient. So at 0th order, it's simply the local equilibrium propagator or local equilibrium Wegener functions. So it has a clear mass shell, and the spin structure is encoded in this P slash. And this at next order, it can be solved from these equations. So it's given by these expressions. Actually, the decomposed form of the solution is already obtained by these authors. And here we are just reproducing it in spinor form. So the vorticity enters through this p tilde slash. So the vorticity enters here. This solution actually gives, so if we trace the Wigner function with gamma I and gamma 5, it gives the polarization of the particles. In fact, if we do that, it gives a contribution proportional to the vorticity and also f prime. So if we further integrate it over momentum, so it leads to a chirovortical effect. So let me now explain why we can ignore the collision term for the previous slide. So the collision term is expressed using the self energy and the Wigner functions. Both quantities can be expanded as a gradient expansions. To the lowest order, so the right-hand side is only has S naught and sigma naught, and this self energy has the following representations. So following diagrammatic representations. This self energy, the hard self energy, comes from splitting of a hard fermion into a hard one and soft photons. This gives the dominant contributions, and so it can be expressed as a integral of these two, one fermion propagator and the photon propagators. And this stressed photon propagator is further can be expressed using the hard fermions, as I explained, because it has the hard fermion has larger phase space. So we have the following representations in terms of off-equilibrium Wigner functions and equilibrium photon propagators. So if we put the lowest order contribution into the right-hand side, it actually so this corresponds to a local collision term. It vanishes identically by detailed balance, and the reason is simple, because S naught and sigma naught is nothing but local, determined by local equilibrium. So so this is also the reason why using free kinetic theory can give the correct result for chirovortical effect. What we want to study is to study the effect of these gradient 1 contributions. So these contributions, these terms gives non-local collision terms. Let me first, for pedagogical reasons, turn off the vorticity and study the approbe fermions in a stationary fluid. So in quasi-particle approximation, the greater and the lesser Wigner functions satisfy the following identities. So their difference is given by the spectral density of the following form. And if there's a perturbation to the fluid, so the perturbation actually is independent of the spectral densities. So the difference of the perturbation is zeros. This leads to the following kinetic equations for the perturbations. So it's a linear homogeneous equations. Since now we don't have any right now we don't have any vorticities. So it's just the right-hand side is just the self energy in equilibrium. So this part, the difference of self energy can be evaluated using can be obtained from these diagrams. So we can imagine this is a probe fermion. So this is delta S, and this is so the self energy comes from this the gluons and the medium fermion, the photons and the medium fermions. So there's a dominant contribution from soft photon exchange due to there's the infrared enhancement when the exchange photon is soft. So by solving these equations, and people obtain this a damping exponential damping behaviors, which is e to the -2 gamma naught t, and this gamma naught is given as follows. So the logarithmic enhancement is visible here, and for QCD, for QED, actually one needs to introduce an infrared cutoff. The reason is the exchange photon can be electric photon or magnetic photon. So the electric photon is fully screened, but the magnetic photon is not fully screened. So this leaves an infrared divergence. So for QCD, the situation is milder because there's another scale, the magnetic scale, which can cut off this infrared divergence. Our goal is by focusing on this infrared divergence that we can actually focus on a particular type of process, which is the Coulomb scatterings. So let us see these. So in both QED and QCD, we have this type of similar processes. One is the Coulomb scattering. So this corresponds to the self energy of photon the fermion self energy of this type. So it's a hard photon split into hard fermion split into hard fermion and soft photons. And for Compton scattering, it's the opposite, split into a soft fermion and hard photons. So for this case, because it involves hard photons, so one would have to introduce kinetic theory for photon as well. However, if we focus on the same infrared divergence as in the previous page, we can actually forget about the Compton scatterings. The reason is the Coulomb scattering has the infrared divergence is unique for the Coulomb scatterings because there's an additional infrared enhancement here due to the Bose enhancement for the soft photons. So if we focus on the infrared divergence, we can forget about Compton scattering for now. So actually, similar decoupling is also used in Hongwu's talk for there. The mechanism is mass suppression of Compton scattering. So now we are ready to introduce probe fermion in a vortical fluid. With vertical corrections on the right-hand side, so on the collision kernel, so there are two types of corrections. One is through corrections to the vertical corrections to the medium fermions, so correspond to this term. And the other is vertical corrections to the soft photons through these terms. It turns out the vertical corrections to the medium fermions vanishes identically. And there's leaving only the vertical corrections to photon self-energies. Only this type of correction remains. Here I would like to show the vertical correction to soft photon self-energies. As I explained earlier, that the self-energy of soft particles is entirely determined the distribution of hard particles, hard fermions in this case. We can use the hard fermion distribution to work out the vertical correction to photon self-energy. So there are spatial component and the temporal spatial component. Both are antisymmetric and purely imaginary. And here the chi is proportional to is of this form. In fact, this vertical correction to photon self-energies satisfy the word identity in a non-trivial way. So it is a balance between the zeroth order self-energy, symmetric zeroth order self-energy, and the anti-symmetric self-energy. So using these, we can put this self-energy corrections to the kinetic equations. So this kinetic equations in spinning form, and we have a new term on the right-hand side. So this term is given by proportional to gamma 1. So this gamma 1 is interaction dependent, and it's actually given, it's a similar type of infrared divergence. So it's proportional to log the biomass over mu. And for QCD, we just replace mu by the magnetic scale. Also, this term is proportional to omega perp, which is the perpendicular component of vorticity to the direction of the probe fermion, the momentum of the probe fermions. So we can solve these equations and obtain the following solutions. So the overall exponential damping factor is from the stationary fluid case. So this always exists. And there are three types of kinds of contributions in the square bracket. So the first one is actually well known. So it's proportional to p slash. So it's nothing but it just means the spin and the momentum is aligned for these terms, and it has opposite sign for right-handed and left-handed fermions. For the second term, it's actually also known. So it's proportional to the vorticity. So the vorticity enters in this p slash, and it's actually independent of the whether it's right-handed or left-handed fermions. So the new term we obtained is this one. So this one is so its sign depends on differs for right-handed and left-handed particles, and it's perpendicular. The direction, the polarization is perpendicular to fermion momentum and vorticities. So both the third term and first term has opposite sign for the chiral fermions. So if we can imagine that if we sum over the left-handed and right-handed contributions, it has to be proportional to the chiral imbalance. So let me let's give a quick look at the physical implication for these terms. So for the first term, although this dependence is well known, but I just learned in this workshop that in Andrea's talk. So although this term appears to average out after we do momentum integral, but it still survives when they consider particle correlations. And the second term it gives just a chiral vortical effect. So it has been widely used to understand the lambda spin polarizations. And the third is what we obtained. So it corresponds to compared to this one. So it is the rotation of polarization along the vorticity axis, and it's dependent on the interactions. So schematically, this is the direction of vorticity, and we have, say, right-handed fermion and left-handed fermions, and the two are rotated in opposite directions. And of course, there's an overall exponential damping factors. So if the damping rate is sufficiently low, so this mode, this perturbation mode may have an effect on the polarizations because they are in points in different directions from the vorticity. So let me summarize. We have used a spin-dependent kinetic series with collisions to study spin-dependent transport. In particular, we obtained a polarization rotation in a vortical QED and QCD plasma. And there are many extensions can be done. So for example, we can consider coupling. So of course, in this work, we ignored Compton scattering for simplicity. To have a more realistic description, we need to include Compton scattering back. This would need coupling to photon kinetic series. And also, the effect can be generalized to study massive fermions, and also the case with electromagnetic field. So of course, there are also other interesting spin-dependent transport, like those that has been presented by Mamoru in the previous talk. It would be interesting to study these spin transport. So with that, I will finish, and thank you very much for your attention.
Okay, thank you very much. And so this is exactly on time, or maybe even earlier. Okay, the questions, Masood, please.
Hi, thanks for the nice talk. I have a question about this damping rate.
Mm-hmm.
This damping rate is essentially, as far as I understand, like this logarithmic part is like logarithm of 1 over g, yeah? Because the Debye mass is also gt, yeah? So,
yes.
In order for this to be damping, you essentially need a weakly coupled regime, yeah?
Yes.
Because otherwise it can be enhancing, not damping, because it changes sign at some place.
Sure.
Yeah. But what temperature, what scale of temperature are you assuming here?
It's high temperature, of course.
High temperature.
So first of all, in order to separate the hard particle and soft particles, the coupling has to be small, and this is necessary for quasi-particle picture to work, and the mean free path is long enough. So this quantity is the coupling also.
I think I lost the speaker's voice.
Shu, are you still there? We should wait. Maybe the connection will be coming back.
Okay.
Yeah, sure. Okay, so your voice was interrupted. So please continue answering. Sure. I cannot hear.
Yeah.
Can I comment on that? Because I'm.
Okay. So you have a comment on this specific point. Okay, please.
Yeah, yes, because of course for this formulation, we need to assume the high temperature and the carbon constants is small in order to make this derivation consistent. So we used hard sum loop observation.
Yes. Okay.
Okay.
So
Thank you.
Then, yeah. Okay, let's go to the next question by Di Lun.
Hi, Shu Lin. Are you still there? Or?
It seems that Shu Lin is speaking, but we cannot hear. But I hope that he can listen to your question.
Or maybe the Fu can also answer because he's also the author of this paper. So anyway, so I think okay. So let me ask you this question. So actually, I have a very technical questions about this word identity you show. Maybe now Shu Lin can, if you still can hear me, can you move your slides to that page? Or maybe he cannot hear me anyway. Okay, I just asked the Fu. So about this, the word identity stuff. Yeah, basically, I think that is also the same as this gauge constraints is coming. I think you choose the Coulomb gauge. So what I want to understand is actually these detailed relations is, to the KMS relation, because on this page, that's right. So basically, as I can see now at this order one, though basically the order of H bar. Okay, page is still changed now. Yeah, this page. Yes, please stop. Yes, yeah, right. So also I read from your papers is basically what you said is that for this at these orders, for this anti-symmetry part, the lesser pi ij or pi alpha beta, it's equals to the minus pi alpha beta is greater, right?
Right.
But for the zeroth order, they will differ from by a kind of Boltzmann factor, right, from the KNS relation. So if the word identity is indeed satisfied, I just wonder how these kind of Boltzmann factors can disappear for this pi alpha betas at the order of H bar, or pi alpha beta 1. Yeah.
Look, KMS conditions only works for equilibrium case. We don't need to use the KMS condition for if it's away. It's a non-equilibrium case. But the word identity is a consequence of gauge invariance. So it's here we don't need to use the KMS condition due to the non-equilibrium contributions.
But wait, but
I'm actually not sure. I'm actually not sure about your. I mean the relation between less and greater self-energy that you just said. Is this what we wrote in?
In this, yes, the form is like in this less and great, we have distribution function that here, and then the first order correction, we have this distribution derivations, but we didn't assume the specific form. So it is not necessary to take the equilibrium case. Only at the zeroth order, you take the equilibrium case. If it's not the equilibrium case, we don't have to use the KMS conditions.
Right, but anyway, I thought in this loop, both these fermions are in equilibrium, no?
No, the fermions are vorticity corrected.
Right, yeah, vorticity corrected, in equilibrium.
Okay,
I mean, in thermal equilibrium.
Yeah, I've been listening always.
Oh, sorry.
Yeah.
So okay, now it's your turn.
No, it's fine. It's fine.
Yeah. So it's in equilibrium with vorticity, right?
Mm-hmm.
Okay, this is a very interesting point, but maybe it takes some time. So even though we don't have a roundtable discussion, but maybe after the formal session, so we can continue discussions.
Okay, no problem. Yeah.
So let's go to the next question by Duke, please.
Yeah, thank you, Shu. This was a very illuminating talk. I'm just trying to understand the relation of your calculation to this non-local collisions that were discussed yesterday. So if I understand it correctly, you have this 2x2 scattering.
Yes.
But you and you perturb around equilibrium. So in some sense, that is also what people have looked at, but there doesn't seem to be any non-locality in your collision term, right? Or
well, there is. So it's probably visible here. So in our approach, the non-locality comes from everything non-local comes from the gradient corrections, vorticity corrections. So it can enter in the exchanged photons or enter in photon in the medium fermions.
Yeah, where do I see this gradient term in? Is it in energy?
So for the fermions, it's actually it's fermions in this form. Let me. So the fermion in this form.
Yeah.
And vorticity correction comes in this p tilde.
I see. Okay, maybe I missed the definition of that. Okay, down there it is.
Yeah. But this part actually, this medium fermion actually doesn't contribute. Only the perturbative self energy of soft photon contributes. So in some sense, it changes it modifies the interactions from the vertical corrections.
Yeah. But
because the interaction is mediated by the photons, so
somehow I had the
self-energy changes.
Yeah, excuse me, sorry. Somehow I had the impression that you have to have a mechanism to convert your vertical correction into spin, and that was somehow not apparent to me here.
Yeah, it's not apparent to me as well. So for now, it's just the gradient corrections to the collision term. And I'm calling the gradient correction as non-local contribution to the.
Yeah, I would think that comes from that term. Okay, anyway, I think I need to read your paper to understand this better. Thank you, though.
Okay. So let's go to the next question by Chum.
Yes, sure. Very nice talk. So my question is similar to Dirk's question. So would you please go to the pi IGA? This is a photon polarization tensor coming from the this loop, the fermion loop. So as I understand, your fermion loop has some vorticity term correction, right? Like
yes,
this is a propagator carries some vorticity. Then you insert back into this photon polarity tensor. Then you get some vorticity dependence. Okay, is it correct? You said this effect, the CVE effect.
So this gives CVE, but I mean the CVE doesn't care about the soft photon. Okay. So this correction to vertical correction to hard fermions is enough to give the standard CVE.
Okay.
But it also gives the correction to soft photon self energy.
So where does this come from? As a dependence on the of the vorticity of this propagator.
Well, actually, this is equivalent to the result obtained by you and Jianhua and the collaborators.
Okay, so
writing it in spinor form, in matrix form, and it's exactly the same as yours.
I see. So
okay, maybe that is a bit too technical point, and so
okay.
Shall we go to the next question by Ho-eun?
Yeah. Thanks for the nice talk. So at some point you mentioned that this solution you call S1 can be obtained just from the streaming term without collision, because collision should vanish. Have you checked that explicitly in your calculation that indeed the collision term vanishes with this solution?
Yes. So what I checked the following. So So if the right-hand side is only gradient 0 terms, so it
yes,
vanishes.
that's the local, yeah. So
yeah, that's
that
just
should be
local.
fine.
But what we consider is when we plug in this gradient corrected S and sigma, so this will give non-vanishing contributions. And this is what we used to solve the equations.
But I understood that this solution S1 you could obtain just from setting the left hand side 0. I think that's how Chun and previous people found the solution to obtain kind of vertical effect, right?
Yes.
So in that case, I understood that is justified because collision term will vanish anyway in the equilibrium,
right.
so that we don't. But
right. So here there's one gradient, and here there's apart from gradient, there's also additional suppression factor in front of self energy E square. So the correction from the gradient correction to the collision term is even higher order.
High order in coupling constant.
The correction we did is has E square in front and also has one gradient.
Yes, but in terms of gradient, it's of the same order, right?
Yeah, in terms of gradient, it's of the same order. That's true.
Right.
But the gradient itself is also E square T, so, right?
Okay.
So overall,
yeah,
coupling it's suppressed.
But isn't it strange that would mean that actually this kind of vertical effect in equilibrium will be modified by interactions? That would.
It will. Yeah, actually, it is the result obtained by Defu and the collaborators. There are the modification radiative corrections to chirovertical conductivity.
Even in, you mean equilibrium, massless
in equilibrium
limit?
In massless limit, right?
That's okay. So that's something that contradicts to my understanding. Okay. Okay. So yeah. So
well, maybe yes.
Yeah. Maybe we. Yeah. Okay. Let me think about it.
Is there any strong argument for the protection of the coefficient? I don't know.
No, it's this hydro computation, right? This second law of thermodynamics.
Yeah, but it doesn't constrain the coefficient of T square.
Oh, you're talking about T square correction?
Yeah, T square. Yeah.
Oh, I see. Okay. Oh, that's well. I mean, there have been also argument about this connection to gravitational anomaly or discrete anomaly,
but
which is also protected. So you're saying that actually there's interaction correction.
Yeah, the Fu and collaborator did explicit loop calculation showing that there are.
Yeah, even without considering gravitation anomaly correction with interaction, there is a correction on T square due to interaction.
Now I think that the discussion is coming to a more and more subtle point. So maybe so we should stop this discussion. Otherwise, it may be endless. Okay. So thank you very much, Shu. Very nice talk.
Thank you. Thank you.